This is the Astronomical Statistics 2023 after I found all that stuff last year in the basement. It inspired me to kind of redo this in a more modern, updated format since computers are a lot better now. There's a lot more we can do, even the average person, than we could do in the 90s with a desktop because, well, we had laptops then, but no one had them. So I've redone that 1990s book, but I restricted it a little bit. This one is more affordable, even though it's full color, because it's nowhere near as thick. It too is 6.5 by 9. All right. Now this is a stock photo that's free, so I just pulled it. It's not my photo. This it's completely royalty free. This I did do. I did this and I sourced it, I think, in the first or second page. I forget where. But I based it off of someone else's work. And I added a few because there were a few that were not on here that are within the 15 light year thing. Now, I pulled back on this book. The first one was within 25 light years, but I didn't want, since it's full color, sorry, excuse me, I did not want this to be massive and cost an arm and a leg. This book is actually cheaper than the 1990s book because it's so much thinner. There's less stuff in here. But we'll go through what is in here. And I just want to show you there's the sun, Sol. I had to add lumen 16. I had to add, where's the other one? WISE 0855. I had to add, there's another one. Anyway, I don't want to spend too much time looking for it. Anyway, this is our solar neighborhood within 15 light years. And this disc right here has to do with right ascension and declination. And those of you that actually look at the night sky might notice that we give those coordinates so you can find the object. And you're going to see them here. I did not put them in the 1997 version, primarily because Word back then, if you wanted to do a superscript or a subscript, I did it on occasion when I really had to, but it was a pain in the butt. It was a pain to find those. And with as many as there are for astronomical statistics, I just avoided it when I could. Now it's not an issue because, if you have Word open, it's like right here and you just click it. Or Publisher, you click it. Maybe with Word it's not there, but for Publisher it is. And this is done in Publisher, okay? But yeah, I did do this one, but like I said, it is based off someone else's. So we're just going to go through a little bit. I'm going to show you some stuff. This one I have a little introduction for you. And this is not in Courier New. This book is in Toma font, which actually for me doing this kind of stuff is my favorite. I like Toma better than Arial or was that Calibri, whatever it is, because in there these lowercase L's do not look like uppercase I's, nor do they look like the number one. All these things look different. So you see, this is what a capital I looks like, and I believe it's Arial. Maybe it is Calibra. An I, capital I, looks exactly the same as a lowercase L, and I didn't want to deal with that crap, so I used Toma. This I'm not going to show you everything in here, obviously, because I want you to buy the book, but there's several sections in here. And this shows you where I got this from. NASA does not care that you use their images for anything. They don't care as long as you say it's from NASA. And that's what I did here. Now, in this, in order to avoid a lot of citations and to keep reading flowing in here, because I do know that turns a lot of average people off as they read scientific papers. The constant citations doesn't turn me off. It helps me find out more stuff, you know? So, but I know for the average reader, it's a pain in the ass. So I put specific citations that weren't my own calculations or based off my old 1990s stuff. I put that at the bottom of that celestial object, its pages, if you will. If it's a, but I use general references for the whole thing, and those are at the very end, and there's several of them. Now, the Galaxy Third Catalog, I actually have a printout of that from the 1990s, and I was going to put that in my 1990s book, but it was already over 300 pages, so I didn't want to make it more. But I'm thinking about putting that for historical purposes just on my website, along with the exoplanets, even though I included that one in my old book. Um, but as you can see, this is about half the length of the other one. Now, this is in full color. I picked extrasolar objects within 4 parsecs instead of 25 light years. 4 parsecs is about 13.05 light years. Okay. I did that so it wouldn't cost an arm and a leg. I also have no table of contents or index for the same reason. An index, I started, like, as I was writing down all the stars and stuff and information, the index probably would have been an additional 15 pages. That's what I was looking at. It's not because I was lazy. I know some people are going to still say I was, but that stuff drives up the book. I have no blank pages between anything here. I wanted to keep the cost more affordable, and this book is more affordable than the 1990s one. It's available in hardcover and paperback, just like the 1990s one. Okay, but I'm going to show you some stuff here. I also didn't include a format page because I figured you could figure it out. All right, so first we go to the sun. So, okay, and as you can see, I've learned a lot about why this is a G25 and not like a G2.55 or something like that since then, because it has to do with the spectra specifically and only. So I'm not trying to fit any square pegs into any round holes here. Okay, so it's whatever the common classification is. A lot of times there's conflict as to what that is. With our sun, there isn't. With most large stars, there isn't. But when you get to smaller K stars and M stars, I'll see sources, and some of them I'll put them there, that listed as a star, say, as a K7.5, and then somebody else says it's M05. I mean, there's overlap. And I was aware of this back in the 90s, but my brain didn't like that stuff back then. Now I accept it. So, just to show you this, this is my actual photo. I took this. It's the only photo of mine in this book. The drawings are all mine, but this is the only picture that's mine. See, I give some planetary data, and as you can see here, this is kind of the format we use. For planetary bodies, so I just decided to toss it in here. That's what it would be. So yeah, that. I'll give you some more information here. That's about what one astronomical unit actually is. We actually locked down how many kilometers an astronomical unit is, I think, back in the early aughts. So measurements have gotten better. So it turns out it's a little further than that. Barely, but their one astronomical unit is the distance between Earth and the Sun. On average. That's what it is, okay? So 1 AU is 1. All right, so, and as you can see, I've added dwarf planets, some of the bigger ones, and just compare them with the moon down here, or Luna. I try to use the actual names of things if they've been named, and I'm aware of that, instead of numbers or common names like or the moon or Earth. Although I do I will admit, I flip back and forth between Earth and Terra a lot. Terra is Earth's name. It just means, well, Earth. Or Earth as in the ground you walk upon, like dirt, stuff like that. But anyway, so Luna is the moon, which means moon. We're so original, aren't we? Relative size of planets. I put this in here for you. These are all from NASA. See, it just says it's from NASA. So I use NASA's images. They are to scale. I do a lot of to scale in this, and I'm going to show you that. Relative size of the dwarf planets, moon and Terra, and Luna. See, I do put Earth here and the Moon, just so you know. And obviously, these three are the only ones we have actual images of. These are all artist renditions, and NASA, unfortunately, never gives their artists any credit, or so rarely do. They do once in a while, so I just put their source down, NASA, Now, you see this a lot. Each one's going to have this. It's a bar, it's a spectrum bar. When you're looking at a star, it's going to be within these color ranges. Okay. Now, a star is always going to look white towards its center or yellow. Okay. The reason for that is because all stars, even if they're over here and emit mostly infrared, or they're over here and they emit mostly ultraviolet, they're still going to illuminate within the visual spectrum. Now, I am also limited on paper as to how I can represent that. I can't show a glaring middle, okay? So the sun falls right in here. Now, you may be like, where's green? Well, there is no green because stars radiate like black bodies, and black bodies do not have green in their spectrums. Do not if you've ever seen hot lava, what is it? It's red, orange, yellow. You'll see some white parts, maybe. Okay, you don't see green because green is not in there. It's all the colors in the middle. And I think the peak is at like 6,200 is white, something like that, 62 or 63. I tried to get this as close to reality as I could. So our sun to us actually looks white. And that's what this is. This I took at solar noon on this date. This is through the atmosphere with a filter on the camera. This is the most realistic color the sun's going to look from without expensive equipment. And as you can see, it does have a yellow outer edge, and it does radiate in a yellowish color. And that's why we call it a yellow star, okay? Even though it looks white. The sun is actually more white, okay? It's closer to this, okay? And what we call red dwarfs actually are orange. So, and what do you call it? Brown dwarfs, they'll actually be red in color, okay? And very bright and hot stars, we like to think of blue as being cold, but actually, as things get hotter and hotter, they turn blue. Okay. Well, unless there's some sort of chemical marker. Okay. I'm not talking about burning certain elements that look certain colors. That's not this. They aren't radiating as black bodies in that case. This is for stuff radiating as black bodies. So, and I do this here. There's Earth to scale. This is to scale. This is to scale. But it's not to scale with these. And you'll see that a lot. I'll have the distance between stars and or planets, between other components, and all the components will be to scale. And the bar is to scale, but the components are not to scale with the bar, obviously, because it wouldn't show up at this scale. You wouldn't see the sun at this scale, okay? You just wouldn't. Oh, and it might actually be a little dot. You wouldn't see Jupiter, and you definitely wouldn't see Earth. So I got rid of the separating binaries or trinaries, and I just went in order from closest to furthest. Now, as you get further out, there's more and more stars, and I can't believe I had to tell grown adults this, none of you guys, but other grown adults this, that the reason why there's more stars is because we live in a three-dimensional universe of space, not a one. As you look in different directions, there's going to be more and more the further you go out. That's why Alpha Centauri are the closest, star system that we know of, or closest system, or Proxima actually is 4.5 light years away. We only have one. Why? Because that's how 3 dimensions of space works, guys. But not you guys. Sorry, it's just because I keep running into that. These numbers are a lot better than they used to be. G25. These are a lot better. These are a lot better. Why? Because the search for exoplanets, quite honestly, that's the only reason why this has gotten any better. I'm going to show you and so here what I did is I did put the right ascension and declination in this catalog. I did not do that in the 90s one. Okay. I just gave the constellation, which I also do here. Where is it? Yeah, Centaurus. Okay. Southern hemisphere is where this one is. And then I put a little map in a light sky, and it's adapted from Sky and Telescope. These are all common use based charts. I do expand them and shrink them as needed and add a little like color just to change it up once in a while. But yeah, those are, and the only time I ever went to Wikipedia was to basically pull these. Okay. And yeah, so that's really it. And I did to like kind of like get my basic lists and stuff, but I tried to avoid Wikipedia, even though their stuff on astronomical statistics is pretty good. It's pretty good, but it's still kind of not official. So I tried to avoid it. And then y'all have to scale with our sun. All right. And the appropriate color. Okay. So wherever it falls here, how it would look through a filter. Not really to the eyes, because I can't do that on paper. There's always going to be a white middle. Okay. To a star. Well, to yellowish, depending on how dim it is. So here's B. And as you can see, the mass of A, I was pretty close when I thought it was 1.08. And now that's our margin of error instead of margin of error 0.1. But I was wrong about B. I thought the period was a little less and they were a little closer, and B was closer to 0.88 solar masses, but it's 0.90. And these are very luminous and large for their spectral class, as where the sun is a little on the low side. Now it has to do with metallicity a lot, because like I said, this is based off of the spectrums. So it's not based off the masses per se. All right. But there is a mass luminosity relationship, and I use that in a lot of calculations. It's in the equation part, which this does have as well. And here I put the orbit as viewed from Earth. So you can check that out. Okay. Here's B compared, and if it's a multiple star system, the multiple parts will be in each component. There's an A, B, and C. Notice I didn't put Alpha Centauri C in here. Why? Because I didn't have a scale. This is such a small piece of paper. Proxima Centauri, or Alpha Centauri C, or just Proxima, is so friggin' far from these two that I couldn't make it to scale. Okay? But this is something new I've added. Orbit of Alpha Centauri B around A. And these red circles, these are where stable planetary orbits can exist, as long as they're near the orbital plane of the two stars and their orbits are nearly circular. Okay? And these are rough calculations. I derived an equation. I'll show it to you. I don't know why it's right, but it seems to work. I even tested it against Sol and Jupiter, and it seems to work. So yeah, anyway, but here's, sometimes I'll do this, put Jupiter's orbit or Earth's orbit or whoever's orbit there. This is to scale the orbit. The bodies are not to scale. They just so they show up, but all the orbits are to scale. Here's the scale bar, 2 AU, astronomical units. I work strictly almost with astronomical units in this. And as most of you know, most orbits are elliptical, not circular. So there is an equation I used to get this eccentricity. The eccentricity, you'll see, is just a unitless number. It tells you how squashed the orbit is, how elliptical it is. Where is it here? Eccentricity. Here. Okay. And this weird thing is, most binary stars that are S-type, what that means is, or I shouldn't say S-type, that's inappropriate use, but widely separated binaries that aren't what we call spectral binaries, which means they're really close, there's two really close to orbiting each other. Their eccentricities are almost always between 0.4 and 0.55. I don't know why that is, but it's that way, and that really hurts the search for extra Terran life, if you will, extraterrestrial life. Okay, but that's a 0.541 orbit. So yeah, as you can see, Alpha Centauri B can be so far away from A that you can probably, well, you could almost fit the whole solar system in there, but it comes so close that you can't. And these two will obviously gravitationally interact. And we model the orbits like this, but in reality, the two are orbiting one another. So it's like two orbits, around each other. But we do it this way for simplicity, and for all intents and purposes, this works. So we use it. Okay. Here's Alpha Centauri C, which is just Proxima. All right, and now we know of two planets around there, and see how far away this is. That's why it's not on this scale, and I didn't see. And I did hear though. I had to put these overlapping one another because relatively they're so close to one another they'd be a single dot if this whole thing was to scale. But remember, these are the bodies are to scale with each other, and this is to scale, but the bodies are not to scale with the astronomical units. Anyway, here, blah, blah, blah. All right, let's move on here. I want to show you some other stuff. Let's go. I not only did stars within 4 parsecs, I did some ones that I thought were interesting. Oh, wait, there's some that were, what do you call it? Not known at the time in the 90s. If there's a planetary system, I'll do that usually. I may or may not do the orbital thing, depends on how easy I can get it to work. See, the ones that are disputed or unconfirmed or discarded are in red. So as you can see, we get a lot of the white in stars, red dwarf. This was not known at the time. Teagardens. This is new. Teagardens star with planets. This Teagardens star wasn't even known to exist in the 90s. Capitans was. This one was. And some of the distances have changed. Some things have changed to kick this just out. And some of the stars just out of this, and some just in. Now, if they were real close to 13.05, I put them in anyway. Okay, this is also known as, I don't think this one was known at the time either, this system. So, yeah. B is I believe B is B is a brown dwarf. This is a brown dwarf classification. And I'm going to show you at the end that some of the M dwarf and brown dwarfs actually overlap. The smallest stars, true stars, can be smaller than the largest brown dwarfs. And that likely has to do with their composition, how they formed, how much of it is what we would consider heavy, rocky material as opposed to just gas. Did they form from collapsing cloud or did they form from accretion? I guarantee you a lot of large brown dwarfs probably formed from accretion. I do not think that is not possible. Okay? But, there's a lot of astronomers that think all stars and brown dwarfs form from collapsing clouds. I don't think that. I think some form more like planets. Brown dwarfs do. Anyway, I digress. So that Kruger 60, I think this is the furthest one. I think this one used to be within 4 parsecs. Now it's a little further. So I include Kruger, A and B. Yeah, there. And I did the system. Here's Jupiter's orbit. Compared, I did not do a stability thing because, there probably isn't an Earth-sized planet around either of these stars. So, at least not within a habitable zone, let's say that, or if at all. And this is my next section. Other interesting, actually, further than 4 parsecs. Usually what this is it's our closest white dwarf that's by itself. We have 2 within 13 parsecs, but they're attached to larger stars. They're in orbit with those, Sirius and Procyon. But this Van Mans is the first one that's by itself, doesn't have a companion. Our closest O star, B star, our closest A star is Sirius, so I don't have that in there. It's within the 13.05 light years, and stuff like that. So stuff that I figured was special, like here's Van Man's star, and I blew up the sun here because Van Man's is a white dwarf, and it would actually look yellow. Sirius B. Uh, Sirius is the closest A star, A class star to us. Its brown or its white dwarf is so hot it would look blue. It's most of its light is in the ultraviolet. We wouldn't even be able to see it, and it's in the very narrow range of ultraviolet. And humans can pick up some ultraviolet. We can. And if you don't have if you're missing a lens in your eye, because our lenses are what filters it. If you're missing a lens in one eye for whatever reason, birth defect or surgery or whatever, you can actually see UV. Okay, so yeah, anyway, I digress. So this one's the, oh, why did I pick Groombridge? Uh, I did a bit. Oh yeah, because we thought there was a planet in the 80s there, and there wasn't. Some of these are close sun-like stars with planets. I wanted to include some with planets. Okay, Vega. Vega, because it's so big, because it rotates so fast. Now, Vega in reality would look very bright white in the middle and blue around the edge and blue on it, but I can't depict that. So this is as close as you can get to that, and it might not even look blue to us. I don't really remember if it does or doesn't. We have also, since I did the 1990s one, we've resolved the surface features of many stars. I think back then we had Betelgeuse, and that was it. This is the. Oh, yeah, see, as you can see, this is one of those ones with some confusion as to what it actually is. And some of them I just picked, and I'll mention it if I do. I'm just like, okay, guys, I'm picking this. Because, the emission lines, depending on who's using them with what equipment, this is the closest giant star to us. And there's our sun, and it's not a very big giant, but it is a giant. It's a 3. What's its mass? Well, but it's probably not going to get much big. Well, no, it will. 1.19, so almost 2 solar masses. No, this will get a lot bigger yet. It's in the early stages. And I put TRAPPIST-1 in there, for obvious reasons. This, multiple planets, you know. Mm-hmm. Sorry, I'm giving away so much in here, and I shouldn't be doing this, but you guys, there's times. But this is the closest sun-like star within 50 light years, or solar twin, if you will. There's different. I'm going to show you that. You know what? Let's just get out of this and let's get into. I want to show you Betelgeuse. Oh yeah, this is the oldest known star in the universe. Of course, all these are in the Milky Way or satellite galaxies because it's all we can really discern with any real accuracy. So yeah. Anyway, Betelgeuse is here. And this I actually see. Betelgeuse should be red in color according to him, but it's orange. It's orange with a yellowish, whitish center. So that's because we do the MK color scheme we do for the peak. But our eyes don't see just the peak light. They see all the light coming in that's in the visible range. So a red dwarf actually looks orange. A red giant looks orange to us, okay? A yellow dwarf like the sun looks, well, white, you know? Oh, yeah. But anyway, I'm going to show you some of the appendices here. All right. These are my appendices, okay? So, this is where I do the spectrum comparison. So you guys can see that. Here's the equations I use. I'm going to fast forward through those. That's how I calculate the eccentricity and all that stuff. This actually appears in my original 90s one, but it's in black and white. Here it's in color for you. And it shows the peak colors, okay? And this is, as you can see, the sun, which would be about right here, peaks within the green of visible light, but there are no green stars, so it appears white or yellowish white. Got HR diagrams here with different type of variable stars. Most white dwarfs are also variable. Here you see the 1A, 1B, 2, 3, 4, 5, 6, and dwarfs are 7. There's different ways of classifying white dwarfs. There's a lot of different ways of classifying things, like Wolf-Rayet stars, but you can still plot them here, and a lot of people will. Okay, so these are your big, big, big giant stars. Okay, they're your massive ones. Okay, so these are supergiants, is what they are. A and B, the one. Okay, and your 3 are just typical giants. 2's between the 2. 4 is a subgiant. We have one of those close to us. It's Procyon. These are stars leaving the main sequence. 5's are the main sequence, and you're going to see some here. Here, I'll go to you here. This is just the color spectrum overlaying, and this is where most stars, visible stars, will plot, or stars easy to see with a telescope. They'll plot here. As you can see, there's not a lot here. There's not a lot here. Almost everything's on the main sequence or leaving it and going only to a giant stage before they go nova. Because most stars are not massive. We like to think of our sun as a typical star, but it's actually not. The only thing it's typical in is the fact it's on the main sequence and like in the middle. It's a medium. It's a median average star. It's not a mean average star. Those of you that know about averages know what I'm talking about. A mean average star is way down here. Okay? A median average star would be our sun. All right. But I do have some here. See, here's our sun. It's kind of in the middle of all this. But so it's a median average, but almost all stars plot down here. Almost all of them. When I say almost all, I shouldn't say that. I should say vast majority. I think it's something like 80% are K or M dwarfs. Now, we refer to our sun as a dwarf. Okay, so all main sequence stars are dwarfs. 6's are subdwarfs. And these are usually stars that are lower in mass. They're what we call, they're a different population star. They're an older star, so they have a lot of less metals in them. So we actually have one close to us. So there we have one of those. See, and here's Procyon B and Sirius B. See, Sirius B is way over here. It's way hot. It's because it's new. I mean, the thing that system, that white dwarf formed relatively recently. Procyon's a little older. Most white dwarfs are in this area here, or they'll be in this area A5 to G5. They're in that area. The universe is not old enough for white dwarfs to have cooled. White dwarfs are dead star cores. The universe is not old enough for them to cool into black dwarfs. So they're all still out there, visible, technically. So yeah, and when a star is born, it lives most of its life here on the main sequence, and then depending on its mass, it will become a giant, supergiant, and either go nova and become a white dwarf, go supernova, become a neutron star or black hole. And you might hear things like pulsars, which are just fast rotating neutron stars. That's all they are. So that's and if they're big enough, they'll become a black hole. But they get to a certain size then, and I'm going to show you one because I think it's cool. The most massive known star, I think it's this guy here. Yeah, he's a Wolf-Rayet. Mass 196 solar masses. This thing, when it dies, it's going to spend almost no time as a giant. It's going to go directly almost to blowing itself to bits. And these stars are so massive, we don't think they leave black holes. They just blow themselves apart. And as you can see here, that's the Wolf-Rayet classification. And if you plot it on the HR diagram, you get an O1.55. So, and I just called it gargantuous, just so I wouldn't have to type this bloody crap over and over. So, That's just, I mean, I say that's not its name. I'm just going to call it Gargantuanus. So, and this would look purple to us. This is almost all this light is in UV. So we actually wouldn't see a very bright white center. We would see a white center, but not very bright because most of the light is in ultraviolet. It's not going to look as white to us. But here's the luminosity compared to the sun, mass compared to the diameter is calculated. The average star for this class up here should be more like 10 radii or 10 diameter. You just remember diameter's entire width of the star, radius is just half, but when you're doing it in solar radius, one solar radius is equal to one solar diameter. So yeah, so then it doesn't matter. But for calculation purposes, just remember that. So, but that's what I calculated, and so I just went with it. But look how small our sun is compared to it. So, and this is a main sequence star. It's main sequence, but oh yeah, look at its lifespan too. I wanted to mention that. Age, less than 20,000 years. Now, this is in a large Magellanic Cloud. Okay, this is where massive stars are forming closest to us, these big bad boys here. In less than 20,000 years, but Steve, the star is huge and massive. Wouldn't it live longer than our sun, which is supposed to live almost 10 billion years? No, bigger stars burn through their fuel a lot faster. They live short, hard lives. So the longest lived stars will be the smallest ones, the M6s, the M9s. Those are going to last, well, the M9s will last trillions of years. Okay, and then they'll just eventually fade out. They won't become white dwarfs. They won't go any nova at all. Then this thing, when it does, it's going to blow itself to bits. Actually, how far away is it? Surface temperature, distance. Where's my distance? I think I might mention this here. Multiples. Oh yeah, it's like 160,000, 63,000 light years away. But we're seeing it as it looked 163,000 years ago. This star now is dead. Today, right now, it's gone. It has refueled the Tarantulan Nebula with its gas and dust. But we're still seeing it from 163,000 years ago when we look at it. So to us, it still looks alive, but the star is long dead. All right, let's move on. I'm going to show you these nomenclature. This is just star catalogs. You'll see that a lot of the prefixes for stars, I have their other designations. They appear in a lot of catalogs, so they'll have other designations. They'll cross each other. There's a good one for that. No, this isn't. Oh, I think this is the largest star by volume. Yeah, anyway. Oh, wait, was that one? Nope. Oh, and the ones that are not within 4 parsecs, I don't. Oh, where are you? No, where's one? Come on, I had to go way back here. Vega, Erdan, Even Mans. Oh, Kruger, I think, is one of them. See all this? This is my 1990s designation, if there is one for it. But yeah, see all these? Yeah, they're everywhere. So yeah, anyway. And we did that. I'm going to wrap this up soon. But I just wanted you guys to take a look at this because I'm proud of these. I just take them as you will. If you can get in, like I said, I'm not an astronomer. I would be considered an amateur astronomer. I do take pictures of astronomy. I've done videos, showing you how you can show that the Earth does rotate from looking at the moon. Stuff like that. And we have stuff like this within 4 parsecs. Now this, like I said, this is statistics. Oh yeah, notice I say independent systems. I don't say stars within, because a lot of these are, see, 2939. This gives you those rogue exoplanets. That's that W0855. Depends on how. According to the IAU's definition of a planet, this would not qualify as a planet. Okay. We don't actually know if this formed in situ, from a collapsed cloud. It's very small. It fits the range of planets, but it may have formed by itself for all we know. So then technically it wouldn't be a planet. But, you know, I don't know. It's not my decision. So, yeah, here's all those. C's, you can see M-class stars are the most common. K's are the second most common. G's, and then you get up here, and because that's where, the universe likes to form small stars. And now you can see the brown dwarfs are a lot less. It's just because we haven't seen them. I guarantee you there's tons of them within 13 light years. We just have only discovered a handful. This is independent systems within. This is the averages. The class mode, or the MK, is M5.5. The mean's M1.5. So you can see these are dim stars that are the average luminosity class. This is main sequence. And this is the size of the average typical star within 4 parsecs. Oh, Hims, are you okay, buddy? This is metallicity. I explained it in the book. Bobby, you okay? You want to play? I'll play with you in a minute. Oh, you do? Okay, he wants to play fetch, so I'm going to wrap this up, guys. These are average typical statistics for stars of those sizes, blah, blah, blah. Anyway, wait. Oh, crap. Hold on. Let me toss to him real quick. I'm going to pause this. I'm going to play with him because I want to go over this. Okay, I got to play fetch with him. So here I take all the stars, 30 closest ones, plot, just throw them here for you. There are multiple systems. I put them close together. You're not done? Oh, no, he's in the other room. So, that's them. Here's your, anyway. So look at that. Now here, these are what we call solar analogs. Okay, they're stars close to what our sun is. All right, they don't have to be singles. They could be multiples. A's and B's. They can be binaries, trinaries, whatever. They're just stars somewhat similar to our sun. I have some notes here. There's really no standard on this, but they're good ones to look for exoplanets and stuff. But these are just a handful of them. And I decided to do this just so you could see how they would look compared to the sun. Solar twins are different. And this is the definitions on this are so wild too. I accept it for the analog because it is a gray area. It's like, what exactly is a star like the sun? Is its main sequence? Yeah, it's a G. Yeah, within a range and all that. But this is a little different. There are no true solar twins. First of all, there's no stars that look just like our sun to us. Okay, there's ones that come close, and here's the standard that I used. All right, it's just one I figured would be close enough. And this one's interesting. Out of all the stars, not only is this one right there the most like the sun, even though it's a G5, it's close to the sun in age, and it has a Jupiter-sized planet about at the distance Jupiter orbits the sun. And that's the only one we detected. So it could have an entire solar system somewhat similar to ours. We don't know. This is probably the most promising out of all of them. Okay. I have a short glossary, so these things like dex, decimal exponent. I explain that stuff if I thought it was necessary, my abbreviations, and some handwritten notes and calculations to just show you the kind of BS I put myself through for this one. And here's the general references. Okay. And so that those were used for just about everything. Anyway, okay. I think I'm going to wrap this up. It's so much longer than the other one. That's it. Please check out my merch. If you have any questions or comments, please leave them below. I would really like some feedback, and I hope you all learned something.